For the method of a variation of a parameter, it is used for a nth order linear differential equation with constant coefficients equals to q of x, a function of x which may or may not contain terms whose linearly independent derivatives are an infinite number. It can be used for whether it has or does not have those condition. So that's what's useful about it. It's like absolute, sort of absolute. And it depends on whether or not you can find the solution, the two linearly independent solutions to the homogeneous counterpart. This part. If you can find those two solutions, then you can set yp, the particular solution of that linearly equation, the original equation, to be equal to u or multiplied by y1 plus u2 multiplied by y2, where both u's are undetermined functions of x, which we will find. Now what we can do is we're going to find yp prime, which is going to be, right, yp prime in this case will be u1 prime y1 plus u2 prime y2 plus u1 y1 prime plus u2 y2 prime. Using basic differentiation, using the product rule, you can also find that yp prime prime is equal to u1 y1 prime prime plus u2 y2 prime prime plus u1 prime y1 prime plus u2 prime y2 prime plus u1 prime, this term, y1 plus u2 prime y2, all primed. Now the reason why we did not expand this derivative is that we will later set the condition that u1 and u2 is defined such that this value over here is equal to 0. Why? Because you will find out that these terms, most of them will simplify except this one and another term. So there will be two terms containing this term over here. So if we set it equals to 0, we can eliminate or we can reduce it from 3 unknown terms to just one unknown term. And we will see right now, because if you just plug it into the differential equation, you get this, right? a2 of u1 prime plus u2 y2 prime plus a2 of u1 prime y1 prime plus u2 prime y2 prime plus a2 of u1 prime y1 prime plus u2 prime y2 prime plus, you get the point, and you get this equation, right? And now we're going to take these terms, right? We're going to take this term with this term with this term, and we're going to factor out the u1. We get this term over here, u2, or in this case it's u1, right? So we get u1 of a2 y1 prime prime plus u1 a2 a1 u1 y1 prime plus a0 of y1, right? Right, so we factored out the u1, and we do the same for the u2 terms, which is this term over here, this term over here, and this term over here. And then we have these three terms over here, right? Which is the terms that I described to you, which is a2 u1 prime y1 prime plus u2 prime y2 prime plus a2 of u1 prime y1 plus u2 prime y2, all primed, plus a1 of the same term again, u1 prime y1 plus u2 prime y2, which is equals to q of x. Because we defined y1 and y2 to be the solutions to this homogeneous counterpart, we can say that these terms all are equals to 0. So this term over here and this term is equal to 0. The first two terms are equals to 0. So you get this equation. And now, if we define u1 prime y1 plus u2 prime y2 to be equals to 0, we can get rid of this term and this term, right? And then we can have this term equals to q of x, which we can solve, or which we can simplify, right? So we get that u1 prime y1 plus u2 prime is equals to 0. We set that and we define the two functions such that it suffices this condition, and we obtain that u1 prime y1 prime, which is this term, plus u2 y2 is equals to q of x over a2. What does this mean? So now we have basically obtained a system of equation, right? Because this is the first thing that we set, right? We defined it to be equals to 0, and from that we solved that this value is equals to q of x over a2. So then, using methods of algebra and some linear algebra, I guess, because it involves some determinants, you find that u1 prime is equal to the determinant of this over this, and that u2 prime is equal to the determinant of this over this. So then you can integrate with respect to x to obtain u1 and u2, and thus also obtain the particular solution, which we defined to be u1 y1 plus u2 y2. And this equation always gives solutions as long as the denominator determinant is not equals to 0, right? And yeah, and if it was nth order, then you would similarly do the same, but now you have n terms, so u1 y1 plus u2 y2 plus u3 y3 till n. And that's basically what the variation of parameters method is, right? And then you can say, right, the method of variation of parameter can also be used for a non-homogeneous linear nth order differential equation with non-constant coefficients, assuming that you know all of the nth independent solutions to the. So basically what all of this means is that you might have a linearly, you might have a function, right, or you might have a linear independent or linear nth order differential equation in the form of fn y n plus fn minus 1 y n minus 1 plus yada 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 plus f1 y prime plus f0 y equals q of x, right? You might have this equation over here, and you can set it equals to 0. Basically, it's non-homogeneous, or its homogeneous counterparts, and if you know all of the nth order or nth linearly independent solutions to that homogeneous counterpart, then you can use the substitution, or we can use the equation over here stated, u1 y1 plus u2 y2 plus yada yada yada, and you can substitute it in, and you can obtain nth, or you can obtain a set of n equations with n unknowns, right? And if it was for the case that n is equals to 2, basically you would obtain the same thing over here, but a2 would be f2 of x. Why? Because you would obtain, right, over here, if we return back, you would obtain this same equation over here, but in this case it will be equals, it would have an, instead of a2, an f2 term, because all of these terms would have f2 and f1, but they would equals to 0 because we set it equals to 0. We set this equals to 0, so it does not matter. So then you would obtain solutions in this form, right? Which is basically the same form that I gave it to you, but in this case a2 is equals to f2 of x.